Hello, it's Stat 134, Lecture 5. So last time we started section 2.1 on the binomial distribution, which consists of n independent Bernoulli p-trials. Remember the binomial formula as shown as given, and the consecutive odds ratio, which is the ratio of the probability of the kth outcome divided by the probability of the k minus 1 outcome. If you just plug in the binomial formula into each of those, you get this expression as boxed. And what's important about this expression is that it can help to show what's shown in red here. So what's shown in red is that for the binomial distribution, the histogram increases exactly when the number of successes is less than np plus p. It decreases when the number of successes is greater than np plus p, and we have two modes exactly when k is equal to np plus p. So I'm not going to take the time to prove this and show how it follows from the consecutive odds ratio, but I've written out this step by step in an appendix to these notes. So if you just go to the end of the notes, oh my goodness, it's disappeared. Well, I'll go put it back in, so don't you worry. There will be an explanation of how this is true, although it is also in the book, but I'll put that back in. So here is an example where n is 5 and p is a quarter. So we see that np plus p is 1.5, and the floor of np plus p is 1. Okay, so this helps you find the mode, because the mode, which is the most likely outcome, is m, where m is this floor of np plus p. It's m if np plus p is not an integer, and it's m or m minus 1, there are two modes, if np plus p is an integer. Okay, so what we're going to do today, we're going to quickly review student responses from last time, then we're going to finish 2.1 on the binomial distribution and start 2.2 on the normal approximation to the binomial. So last time we had a concept test. 10 cards are dealt off the top of a well-shuffled deck. The binomial formula doesn't apply to find the chance of getting exactly 3 diamonds, because A, the probability of a trial being successful changes, B, the trials aren't independent, C, there isn't a fixed number of trials, or D, more than one of the above. So the answer here is that the trials aren't independent, but there was some confusion about the difference between unconditional and conditional probabilities. So just remember that, let's say the trial that your second card is a diamond. So that unconditional probability has no dependence on what the first card or any of the other cards are. So the chance that the second card is a diamond, there are 13 diamonds in the deck, so it's 13 out of 52, or 1/4. So that is an unconditional probability. Compare that with a conditional probability, where you may condition on what that first card is. So a student writes, there are 10 trials, but the probability the card is a diamond depends on the previous cards, so both A and B are true. So that is not correct. Another person says A and B are literally talking about the same thing, literally. The chances of a single trial depends on results from the previous ones, so that is incorrect as well. The unconditional probability of getting so it's a diamond, is always 1/13. If we were drawing from 2 decks of cards having different numbers of diamonds, then A would be false. That's correct. Okay, so now we're going to start section 2.1. These are histograms of the binomial distribution for different n, and different p's. So one thing to note is that some of these distributions have two modes and some have a single mode. So one may ask, what's the smallest p such that n is a mode, and n is the furthest bar. So what's the smallest p that happens? So for example, if you look at n is 3, p would be 3/4. If you look at n is 6, p would be 7/8. Okay, so let's just take a look at this. What's the mode in each of the following scenarios? So for example, if np plus p is 2, okay, if np plus p is 2, then I know I have I know I have two modes, right? Because the floor of np plus p is, because np plus p is an integer, I have two modes, and the mode is going to be m and m minus 1. So in this case, 1 and 2. If, for example, if np plus p is between n minus 1 and n, then I know I have a single mode, and that mode would be the floor of np plus p, which in this case is n minus 1. If I have np plus p between n and n plus 1, then I know that I have one mode and it must be n, right? So we have 2, we have n minus 1, we have n. So you can answer the question for each n, what's the smallest p such that n is the most likely number of successes, right? And so we know that for n to be the mode, np plus p must be equal to n. And so you can solve that for p, and you get p is n over n plus 1. Now the mode is a measure of the center of your data. The true center of your data is the expectation, or the mean. We'll show in chapter 3 that the mean has the formula np. This isn't usually an integer. So for example, here's the histogram for the binomial 5 1/2. This has two modes and the mean is right in between. So if the mean is an integer, is it the mode? So the answer is yes, right? Because if the mean's an integer, that means that np is an integer. So np plus p is not an integer. That means we have a single mode, and the floor of that must be np, which is the mean. So another fact is that the average spread around the mean, which is called the standard deviation, is the square root of npq, where q is 1 minus p. So notice that the spread around the mean gets larger as n gets bigger, as you can see from this diagram here. For binomial n 1/2, it gets more spread out as n gets larger. And so I ask then the concept test question: a fair coin is tossed and you win $1 if there's exactly 50% heads. Which is better, 10 tosses or 100 tosses? Well, for 10 tosses, you're trying to get the middle exactly, and there's less spread, so it's going to be more likely that you would do that. So it's A, and you can actually use the binomial formula to figure out what those probabilities are exactly. Second question, a fair coin's tossed and you win $1 if you get between 45% and 55% heads. Which is better, 10 tosses or 100 tosses? So this actually follows from the weak law of large numbers. So as you get more tosses, the proportion converges, the proportion of heads converges to in this case 0.5, and so between 45 to 55% may represent like this. So this might be 45% to 55%. So to be in this interval here, you want to have as many tosses as possible. So right here, 0.55, 0.45. Okay, so next thing, the normal approximation to the binomial. So oftentimes using the binomial formula is a pain. For example, if you want to find what's the chance of having between A and B successes, you'd have to compute all of the areas of these rectangles here, which is a whole lot of binomial formulas. So instead, if we approximate the binomial distribution, this histogram, by this curve called a normal distribution, you can just calculate it as the area between the left and the right here. There is what's called a continuity correction here. We've added 1/2 to B and we've subtracted 1/2 from A because the blocks are always width 1 and the integer is in the middle of it. So that's why we subtract 1/2 and add 1/2. But we'll talk about continuity correction next class. So the normal curve has this formula, and the important thing about this formula is that it has two parameters: mu, the mean, and sigma, the standard deviation. Using some calculus, you can show that it has two inflection points at mu plus or minus sigma, and almost all the data is between mu plus or minus 3 sigma. So now we can standardize this this normal curve to get the standard normal curve by making a change of coordinates by subtracting from x the mean and dividing by the standard deviation sigma. This has the effect of making mu 0 and sigma 1. We have a new density formula, as it's called, which is the function describing the curve given here, which is called the standard normal curve. And the cumulative distribution function, or the CDF, is the area to the left of z. So capital phi of z you can find by integrating, well, you can't, it is the integral from minus infinity to z of the density function, but this doesn't have a closed form. So instead, we're going to use a lookup table, or you can use a computer to find that. So now, before I show you how to use this normal table, note that the normal table will only have positive values of z. So, but that's not really a big problem, because to find phi of minus z, just note that that's just 1 minus phi of z, where z is positive. So you can always find phi of a negative number. So here's the normal table. So let's say we want to find the area between 1 and minus 1. So that would be phi of 1 minus phi of minus 1. The reason for that, just look above here. I've drawn what phi of 1 is, what phi of minus 1 is. So phi of 1 minus phi of minus 1 is exactly the area in between that we want. So phi of minus 1 is 1 minus phi of 1. So this is 2 phi of 1 minus 1. And to find phi of 1, you just you find 1.0, and then the second decimal is at the top column here. So that gives me 0.8413. So 2 times 0.8413 minus 1 is 0.68. So 68% of your data is between minus 1 and 1. Similarly, check that 95%